Okay, so because today is officially the last day of class, this is what next week looks like. The rest of this week looks like for me. I emailed this to you on Friday. I have office hours later today, tomorrow afternoon, and then two different times on Wednesday. Our exam is Thursday morning at 8 o'clock. I'm sorry, I didn't make the final schedule. I have not had an 8 a.m. exam ever. So just learn to deal with it. What questions do you have about the final?
You write out all of the, like, working equations for flux element?
There are, I believe, 5 net different versions of flux equation. So the primary version of flux is the flux across a surface. So that's F dot NDS. That's the amount of the vector field that goes perpendicular to the surface itself. That's why we do the dot product with N. The DS with the vector hat above it is a shorthand for that, but it's the same thing. Now, how do I evaluate this integral? That's the question. How do I evaluate this integral? That's going to depend on S. So if S is parametric, then this integral becomes the integral of F dot RU cross RV, and then it's either du dv or dv du. And D is the domain for U and V where S lives. Right? Now you can get that the long way by working out the normal vector being RU cross RV over the length of RU cross RV, but the DS also has that length in it, so those cancel. If my surface is given instead by X and Y, I can do the same thing, but then the normal vector part is going to be that negative GX I negative GY J plus K. But if I write F as PQR, then this integral is equal to minus P GX minus Q GY plus R dA. And that's literally just taking the actual dot product between those two pieces. Better?
On question 4 in the final exam review, it says use the divergence theorem to find the.
Right, because the divergence theorem says that if S is a closed surface, then the double integral on S f dot ds is equal to the triple integral of E divergence of f dv, where that surface is the boundary surface. So all of those are the flux, but the divergence theorem says I do a triple instead of a double. Instead of looking on the edge, I can look inside. But it's only the flux because it's this integral we're trying to evaluate. I don't remember what the surface is for that problem. Can you tell me what it says?
Region that lies between the cylinders x squared plus y squared equals 4, x squared plus y squared equals 9, and the planes d equals -1 and d equals -2.
So if I were thinking of that as a surface, it would have four different surfaces: the inner cylinder, the outer cylinder, the top ring, and the bottom ring. And doing four surface integrals, yeah. On the other hand, doing a volume integral, it's going to be easier in cylindrical coordinates because it's between two circles, and z goes from -1 to 3. So it's a lot easier to do the volume integral than it is to do the surface integral for the flux. But I really could do the surface integral if I was that much of a masochist. I'm not.
I've been just finding it hard to kind of know when to use what, if that makes sense.
Okay, in almost all of these problems with Stokes' theorem and Green's theorem and the divergence theorem, we're asked about an equivalence, right? So this is the divergence theorem. And then Stokes says that the integral around a curve f dot dr is the same as the integral on the surface of curl of f dot nds, which is a flux integral, but it's not the flux of the vector field, it's the flux of the curl. So it's a different thing that we're measuring to go around the edge. And Green's theorem is the part of the curl that's in just K. So that's QX minus PY dA. So here's the most likely statement. If I ask you to use one of these theorems to find something, it's almost always, I want you to do the switch and use the other integral. So if I'm asking you to find the flux, then I want you to do the divergence integral. If I'm asking you to find the work, then I want you to do the surface integral or the double integral instead. Simply because the whole point is to rig the problem in a way that I'm like, oh, well, that's actually a lot easier to do it that way. Because most of the time, if I were to give you a line integral and say, I want you to do this the long way, the line integral better be very easy to do. Or if I say, I want you to do this surface integral, I want you to do the line integral instead. If it says use Stokes' theorem, If it doesn't say which one of these to use, I'm probably going to do it the long way. Unless I know something about this particular surface or curve or vector field. How do I know which one to do? I don't. That's why they say use whatever theorem. That's actually the hardest part in almost all of this. What rule is the right rule? But we said that same thing back in Calc 2, didn't we? What integral trick should I use to do this integral? Should I use trig substitution, u substitution, integration by parts, partial fractions? There were so many different tricks, right? Here's a series. Does it converge? Which of the different rules do I want to use? Which integral trick do I want to use? I'm going to rig problems at this point because it doesn't make sense otherwise for me to ask you, do you know how to use this theorem? And then say, well, which one of them should you use? Stats classes are like that, right? Which distribution should this be? Hypergeometric, geometric, exponential, normal, I don't know. That's why I rigged these problems right now. Almost always, if I'm asking you to find one thing, I want you to use the other and vice versa. More questions?
So if Green's theorem is for work and the divergence is for flux, what is Stokes? Is that also work?
Yeah, because it's still measuring the same integral that Green's theorem is, but the difference between Green's theorem and Stokes theorem is that Green's theorem only works in the plane, and Stokes theorem works for vector fields in 3D. Green's theorem and Stokes theorem are really the same theorem. They're just flat versus lifted, 2D versus 3D. And that's why this piece is the piece that comes from the curl. Because when I do the curl for just a two-dimensional vector field, that's going to give me 0. That's going to give me 0. That's the only part that comes from QX minus Q1. So really, this is the curl, but since my object is already in 2 dimensions, there's no n dot ds part, it's 1 dot dA. Because my normal vector will be going straight up. It took me quite a long time to see that these two were really the same. And that really all Stokes' theorem does is generalize Green's theorem from flat to not flat. And then that same Stokes' theorem actually works in many dimensions. That's the version that we use everywhere else. They don't even call it Green's theorem anymore. They just call it Stokes' theorem. If you're outside the plane, it's Stokes' theorem. More questions? Or cylindrical, yes. Once it's dV, I can do it in any coordinate system I want. As long as I insert the proper Jacobian, right? So when I'm doing cylindrical, it's r dr d theta dz. When I'm doing spherical, it's rho squared sine phi, d rho d theta d phi. If I was picking some other transformation, I just need to make sure that the Jacobian went in there properly. But that would require me to figure out what the region was. Wasn't that just so much fun in chapter 15? No, it was not. Just like this surface area integral here could either be in X and Y or U and V. We just have to adjust the domain S D that we're working on. Exactly. If I had U and V, then this piece right here is taking into account that Jacobian transformation. It is. If there was a shorter way to do it, we'd do it that way. But we did this in U substitutions also. In a sense, that's what we're doing every time we do that du part of a U substitution, right? Right? That's really this same adjustment is really a Jacobian. It's just a one variable Jacobian rather than 2 or 3. It's exactly that same change of frame that we did with from parametric to U and V is really kind of uncoiling that shape and laying it down in U and V and then adjusting for how the boxes changed. Here, I'm just adjusting for how the length changed. And in PV, I'm adjusting for how that box, the three-dimensional little cube, the x, y, z, got changed. And that's the most powerful piece of all of this, is that all I'm doing as I rewrite these things is adjusting for the distortion brought in by changing my coordinate system. Even if I'm just going from X to U. Hey. There are times when I really wish that I could tell the students in Calc 1 that it all hangs together in the same level, when most of the students in Calc 1 are like, just get me through this and out of here. There's a contest. This summer will be the 4th contest. The guy who runs the Blue One Brown channel, Grant Sanderson, is putting together a contest for teachers. And he wants an explanation of something that is useful in the classroom. And my brain said, this idea of a Jacobian being a transformation that makes everything easier would be useful. It would only be useful to people at Calc 3 and above. I really want to do this, but I had way too much to do this summer, so I'm not going to do it. But still, it's one of those things that should get out there in the universe at some point. Anyhow, there are a lot of different places and a lot of different pieces once you get to that level of abstraction. That just, it's really the same thing, isn't it? Well, yes, it really is the same thing. You didn't take abstract algebra. We did the same thing there. Oh, no, really. Modular arithmetic, permutations, group terminology, they're all the same thing. They just don't look like it at first. More question. Yes. Would give me the same answer as the divergence theorem, yes, because this is the same as the F dot N. That's what this little vector hat on the S means. It makes my teeth hurt every time I write that down. You should see the dot differential is not a dot value. Yeah, kind of, because it's a dr here with the hat on it. So a ds there with a hat on it. I get it, but oh, I don't like it.
Are we gonna cancel those are just gonna be the crossfire between RU and RV? Or
In this case, yes. Well, because here it was something else, right?
well, yeah.
Yes,
Yeah.
the length, because n is always a unit vector, it's a unit normal. It's gonna have the length on the bottom, but then ds also has the length in it. So when I do it for the R, the parametric version, S is R of UV. Hats don't go there, the hat goes there. Then N is RU cross RV over length of RU cross RV, but DS is length of RU cross RV dA, so those pieces are going to cancel. And when I do it in G of XY, then my normal vector is minus GXI minus GYJ plus 1K over square root GX squared GY squared 1, right? But DS is square root GX squared plus GY squared plus 1 dA. And again, those pieces cancel.
That's yeah. Where is that coming from?
That comes from our tangent plane.
Yeah.
I've got my surface, right? And I've got a point, and I've got partial with respect to X and partial with respect to Y on that. Yes? So if I make the little tangent plane, it's Z minus Z0 equals GX at the point X0, Y0, X minus X0 plus GY X0, Y0, Y minus Y0, right? But then I move all of that over to the other side. So the GX is negative and the GY is negative, and this has got a coefficient of +1. So the vector has minus GX in the I direction, minus GJ in the Y direction, minus GY in the J direction, plus 1K. Chapter 14, we did tangent planes. All of a sudden, here it is again, it's the same damn piece.
Negative, why is it? Or the opposite direction.
The only thing that the reason those are negative is that I want this one to be positive. If I move that over here, then I would have a downward orientation, that would be negative, wouldn't it? We made the decision that the upward oriented normal was the one we wanted. So really, I wanted to show you that. And that's the only reason you keep this one positive. It works, honest. But if we had made the convention that we wanted it to be downward, that would be fine. And then we'd have positive gx, positive gy minus k. The bottom would still be the same, right? Because the distortion area, everything gets squared. It would just turn the direction of the normal vector over. By the way, that's the same convention for what's positive and what's negative for current, magnetic fields, all of that. That's the same convention. The Pauli exclusion principle, where one electron is up and one electron is down, is exactly the same spin, being positively oriented, negatively oriented. Somebody made a decision this hand, and we've stuck with it ever since. I guess they didn't want too many of us to be sinners. That's the origin of a left, right? One is on the right or on the wrong, thus sinister. That edge I would see. All right, more questions. Crap, it's through my head some days.
With the review.
Mhm.
the file,
Mhm.
the-
Like 2 minutes after we get out of here. 16, 7, 8, and 9, and the review sheet key will all go up as soon as we end class. I want you to have all of the study. And my goal is to have everything of yours graded no later than this point in my office hours tomorrow, so that I can get it back to you by the time you're ready to take the exam. If I get them done today, I'll get them done today and then tell you about it, but depends on how many people come to my office hours this afternoon. Yes.
What is the double integral as of one?
Okay, so the double integral of 1 ds is the area of S.
So that if S isn't cut dry.
No, I would actually only use that formula if I'm actually asked to find the area. But I could just as easy, depending on the surface, I could use other formulas for the area. But if my area is weird, that's probably the best way to find the area of it, right? Integral 1 ds. Now, realize though that that is equivalent to those two formulas, because that's what ds is. And those were our surface area formulas. So if I remember this is ds, I think that's easier. But when we did arc lengths, we had like 4 different versions of arc length, right? But they're all really d little s. Which coordinate system am I in? Same thing. Am I in Cartesian? Am I in parametric? Let's make it rock and roll.
16.8 question 10, we did in the Q&A.
Yes.
So there's like, obviously you do it in polar eventually,
Yes.
but what time is the best? Because
Well, if I am looking at the way the problem is set up, it's asking me to find this integral. And it says use Stokes. So I'm going to convert that to this. And I'm going to work all of this stuff out first. And then I'm going to switch. Because everything in this problem is given in X and Y, right?
yeah,
So I think I need to know what the curl is. I need to know what the normal vector ds is. And then I remember to myself, okay, this is the flux integral. So it's going to be that integral, right? So I can say, okay, wait a minute. Once I know what the curl of the vector field is, that'll be the P, Q, and R. Notice that's different. That's not this P, Q, and R from F. That's the P, Q, and R from the curl. So I'd have to work that out first. Once I do that, then this integral is all in X and Y. That's where I make the switch. Because now I say to myself, oh, this is part of a thing living over a circle. Let's do it in R and theta. I think it would be much harder to make that switch any earlier because you'd still have Z floating around in the problem. I have to make the Z substitution for Y plus 2. And then I can turn it all into the R and theta polar coordinates. That's the word I wanted. I'm also the kind of person who's willing to wait and do my coordinate change until I'm like, okay, now this is actually the integral I want to calculate. That's what I would change. Yes,
Oh, same one, you switch it to polar, do you, for the A, do you still do R and done?
I was dealing with X and Y. I'm saying, oh, this is the circle, let's move it into polar and use the Jacobian for transformation. But it's a unit circle, right? It's a circle of radius 1. So I know I'm going to go 0 to 1, 0 to 2 pi. Because it's x squared plus y squared equals 1 for the cylinder. Sixteen chapters. 16 chapters. We did it all. I will see you all on Wednesday. A wonderful rest of your day. Thursday. Yes, our exam is Thursday. The other exam is Wednesday. Our exam is Thursday. I will see you Wednesday if you want. I have office hours. You can come by. But the exam is Thursday at 8 o'clock in the morning. I'll be here. No, over in Lynch, room 106. It should be on the invitation. No, I definitely